Welcome everyone, Ninad Gaikwad here again, and this is the third lecture of a power electronic simulation series. And today we are going to study a new device. It is a Thyristor. Okay, let's start. So this is the symbol of the Thyristor. It is similar to that of the diode. The triangle, the vertical line. The only difference is the gate terminal. Okay. And the physical construction is shown in this diagram. It consists of two diodes in series, if we see it in that way. So this is the P layer, one N layer, another P layer, and then an N layer. Okay, this is the anode, this is the cathode, and this is the gate terminal at the second P layer. Okay. A conventional current flow is given in this direction from anode to the cathode, as similar to that of the diode. The thyristor is also a unidirectional device that current will only flow from anode to cathode and never from cathode to anode. Okay, let us see how it works. It is always good to explain the thyristor in terms of the two transistor analogy. This is the thyristor. It consists of four layers of semiconductor. One is the P layer, another N layer, another P layer, and then an N layer. So in total, four layers, two P layers, interspersed by two N layers. So this is the anode, the cathode, and the gate. Okay, this can be represented by this diagram. This is the first transistor. This is the second transistor. The first transistor TR1 is a PNP transistor. TR2, the second transistor, is an NPN transistor. Okay, so we can now see that the base of TR1 is connected to the collector of TR2. Similarly, the base of the TR2 is connected to the collector of TR1. Okay, and in this diagram we should see that there are three junctions. The first one, this junction, we can call it J1. This junction between N and P is J2, and the third junction between P and N near the cathode is J3. Okay, so now if we consider them to be two transistors, and now when does a transistor start conducting? Only when there is some base current. Okay, it has to have some base current. Only then can a transistor conduct. So this is the gate signal. Okay, and if we provide a positive potential over here, there would be some current Ig, that is gate current, flowing into this, that is the base of TR2, or we can also say a positive current will flow from P layer through the junction J3 and N. Okay, but let's see what is actually going on. As Ig is present for TR2, the transistor starts conducting. There will be a current flowing in this direction. As there is a current flowing in this direction, the current from the anode flows through its emitter, then the base, and from here the circuit completes till the cathode. Okay, but as the TR1 has a base current now, because a current flows like this, which is actually caused due to the gate current IG. Therefore, TR1 also starts conducting. That is, current flows from anode to the emitter to the base and then to the collector of TR1, and this collector is connected to the base of TR2, as we can see here. So what is happening actually is that once the gate signal is given, the two transistors start feeding each other and get latched. This is called regenerative latching. Okay? Because of this regenerative latching, only a small amount of gate signal is required in the time domain. That is, you can just give a small pulse at the gate, and once the two transistors or the current starts flowing, the current gets latched. That is, the two transistors start feeding each other regeneratively, and you don't no longer require the gate signal. Okay, so the Thyristor is a latching device. Once it gets latched to that current, we cannot use the gate signal to unlatch it. Okay, we'll see how to stop conduction in an Thyristor. Okay, let's go ahead. These are the characteristics or the VI characteristics of the Thyristor. Very similar to that of the diode and exactly similar in the reverse side. Okay, so this is the current axis, this is the voltage axis, this side is the forward voltage side, this side is the reverse voltage side. What is forward voltage? Forward voltage is when anode is positive with respect to cathode, and negative voltage is when cathode is positive with respect to anode. Okay, so let us see what are the different biasing conditions for the Thyristor. First one is forward blocking. Now what happens in the forward blocking region? As it is in the forward direction, anode is positively charged, cathode is negatively charged, and there is no gate pulse. So junction J1 is forward biased, junction J3 is forward biased, junction J2 is reverse biased. Because of this junction J2, there is no passage of current to the device. Okay, and this can be seen over here. As we increase voltage without giving a gate signal, the current remains very low up till a very high voltage. But what happens at this voltage? This is a forward breakover voltage. This is the voltage when the minority carriers have enough energy to have a avalanche breakdown at junction J2, destroying the crystal of the semiconductor. Okay, we don't want our thyristor to have a forward voltage beyond this level. Okay, so in forward blocking, J1 and J3 are forward biased, but no current flows as J2 is reverse biased. This can be seen over here. But let us see the next biasing condition, the forward conduction. It is in the forward direction, so anode is positively charged, cathode is negatively charged, and there is a positive gate signal. Okay, so once you apply a positive gate signal, this junction J2 becomes forward biased. Once this junction becomes forward biased, J1, J2, J3 all become forward biased and current flows from anode to cathode across these three junctions. Okay, let us see what happens. Now we can see forward conduction as this. This is the forward conduction. This is the point when the gate is triggered on, and as the gate is triggered, the thyristor starts conducting current. Okay, this is a holding current level. There is another level called as latching current. Once the current through the device is greater than the latching current, the device is in the on state, and over here it acts as a linear device. Okay, and always remember the holding current is lesser than the latching current. Okay, we'll see what is the implication of holding current and latching current. Okay, the next biasing condition is reverse blocking. So as it is in the reverse direction, the cathode is positive, the anode is negative, and we don't consider gate, or we don't apply gate in the negative direction. So what is happening over here? The junction J1 and J3 are negatively charged. I'm sorry, they are reverse biased, and the junction J2 is forward biased. This is because cathode is positively charged and anode is negatively charged. As two junctions are reverse biased, there is no current flowing through the device. There is no conduction. And this is known as reverse blocking region. It is similar to that of the diode. So if you give a reverse voltage to a thyristor, you will not get conduction, and it is seen in this graph, in this part. You keep on increasing the negative voltage, your current remains very small, and this small currents, even over here and even over here, are actually provided by the minority carriers. Now, what are minority carriers? Minority carriers are, for instance, in this p-type region, we have excess holes. So holes in a p-type region are majority carriers, but in the depletion layer, in the p-type region, there will be some electrons due to diffusion. These electrons in the p region will then become or be called as minority carriers. Okay, so we have a forward blocking region, a forward conducting region, and conduction is possible only due to gate triggering. And the last one is the reverse breakdown, similar to that of the diode. Once a voltage level in the reverse direction is increased, or voltage becomes greater than that level, The junctions J1 and J2 undergo avalanche breakdown due to the highly energized minority carriers. This destroys the crystal structure and your device becomes useless. And as we can see, the current keeps on increasing without an increase in voltage, and the device is ruined. We never want a thyristor to work in this region. But of course, there is a special type of device called as a Zener diode which works in this region, and it acts as a voltage regulator. But it is not part of a course right now, but if time permits, we'll cover that too. Okay? So this is all about the characteristics of thyristors. Okay, let's go ahead. Turn on and turn off. Okay, so as we have seen, we turn on the thyristor in the forward region, and to turn on, we provide a gate signal, and this gate signal causes regenerative latching of the internal transistors. Hmm? And then the current is maintained above latching current. Okay, but how to turn off or turn on thyristor? Because the gate signal cannot be used to control the turn off of the thyristor. So the device cannot be turned off by removing gate signal due to the regenerative feedback of the internal transistors. Hence, only a pulse signal is required to bring device into conduction. It has to be turned off by external means like so. Now, if we have to turn off the thyristor, we can do it in a couple of different ways. Firstly, we can make the current through the thyristor lower than the holding current. Okay, so if a thyristor is conducting and it is conducting this much current, okay, so in order to stop or turn off this thyristor, we have to do something and bring the current from this level below the holding current, and then the thyristor would be turned off. Okay. Secondly, we can turn off the device by changing the polarity of the device. That is, by reverse blocking it. That is, we can put positive charge on the cathode and negative charge on the anode, and this would effectively reduce the current through the device below the holding level, and hence the thyristor would be turned off. Okay. Usually, external commutation circuitry is used to make this current in device lower than holding current, or devices are line commutated. That is, devices are turned off during negative half cycles of line voltage. We will see line commutated devices during rectification. Okay, but we should know that a thyristor cannot be turned off by using the gate signal. It can only be turned on. And most importantly, the gate signal required has to be just a pulse. You don't require the gate signal to be present for the entire duration of conduction. It is useless. Okay, let's go ahead. So important ratings, similar to that of a diode, we have three ratings, one extra rating for Thyristor because of the J2 junction, the forward breakover voltage, rated current, and reverse breakdown voltage. So, a thyristor cannot carry infinite amounts of current. It has some rating. If we cross that rating, it would be damaged due to thermal heating. Reverse breakdown voltage. If we apply reverse voltages greater than reverse breakdown voltage, junctions J1 and J3 will undergo avalanche breakdown and the device would be ruined. Forward breakover voltage. If the voltage level goes beyond forward breakover voltage, at that point, junction J2 will undergo avalanche breakdown and hence the crystal structure would be broken. So we have to keep in mind these ratings while selecting a thyristor for our application. Okay, let's go ahead. Applications. So thyristors are mostly used in controlled rectifiers. They are used in high-speed switching. They can be used in place of electromechanical relays. They are switches. So wherever you want a switch, you can use a rectifier or a thyristor. Thyristor is a very robust power electronic device. Okay? It is a low frequency, high power device. Okay? And it is primarily used for controlled rectification. We'll see this in future lectures. We'll create some really good simulations and we'll study this in detail. Okay, so this was all about thyristors. Thank you and see you soon.